Okay, so magnesium and chlorine. Will, what'd you get for the type of bond between magnesium and chlorine? Ionic. What was the difference you came up with? Yeah, it's good to know the difference so that we can talk about it in case we do get a wrong answer. We can talk about it. 1.85. So the difference between these two would be 1.85. So anything above 1.7 is going to be considered ionic in nature.
Oh, it's one of those days where it doesn't want to work.
Okay, Will, what'd you get for a difference again?
1.85.
1.85. So anything again above 7 it'd be ionic. You can also, guys, use your chart. So you guys have this chart. You can use it if you can decipher what it means. Go ahead and get the chart out if you don't have it out, so that we can find what 1.85 would be on our folded periodic table. So if we look at 1.85, that kind of rounds up to 9. That's 59% ionic in character, is what they say.
Where do you see that?
Okay, it's up above where it says percentage ionic character of a single chemical bond. We look at differences in electronegativities. And once we look at the difference in electronegativities, we find 1.9 is 59%. So anything above 50%, if you notice 1.7 is kind of cut off for there. It's like at 51%. So anything that's above 50% we say is ionic. That's probably not the best way to say it. Okay? It's kind of like Carter. If you do a couple things poorly and on a day, and then you do a couple things well in a day, and say maybe you did 3 things not really well and 2 things really well, and then I say, Carter, you're a terrible student. What is your problem? But then the next day you do 3 good things and 2 things not very good, and I say, Carter, you're the greatest student today. I cannot believe how great you are. And what's the difference? There wasn't hardly any difference there, right? There wasn't. So to say somebody's great or somebody's poor based upon a very little difference, 51% versus 49%. Because if it's 49% difference, what kind of bond would we say it would be? Covalent. And you say, well, the only difference is just a minute amount of points difference. And so, but that's our guidelines, and that's what we're going to use. Okay? That's what we're going to use. Anything. Now, the higher difference it has, the more ionic character it will be. So this is all ionic character. What is 0 ionic character? If we had a compound that had no ionic character, it was 0% ionic character. What's the difference? What is it? Nothing. No difference. So what elements, when we bond them together, would have no difference in their electronegativities? The same element. We bond the same element together, like 2 fluorines, to make fluorine gas, F2. It is pure nonpolar. Okay? Purely nonpolar. Okay? If we have a difference, and the biggest difference we could have is 3.2, then that would be the highest ionic character. There would be very, very little covalent characteristics it would have. Okay? Now we'll talk about later on about these characteristics they'll have. Do they dissolve in water? Do they dissolve in like acetone, which is a non-polar solvent? Are they brittle? Do they conduct electricity? We go through a lab where you're going to do that. I think next week would be a good time to have one of those labs. Short week, be a good week to do that. We'll probably have it, I would say probably Monday, Tuesday. Be a good day to have one of those. All right. Phosphorus and sulfur. Okay, Kendall, what'd you get for that one?
It's 4 bonding.
Okay, what was the difference?
0.37.
0.37? Does everybody else have 0.37? 0.39? It's still going to be polar covalent. Okay? Now, what is the cutoff between nonpolar and polar? 0.3. Right? 0.3 is the cutoff.
What if it's 0.3?
Okay, that's a good question. It's 0.3. You would say either polar or nonpolar, and then have your answer there, because it's right. It's kind of one of those deals where it's right on the line, 50-50. What are you going to do? Which one is it? Okay, so if it's right on the line, you could say nonpolar covalent, polar covalent would be fine. Either way. Okay, but do you think this is much of a polar bond if it's only 0.09 difference from the cutoff? No, it's not very polar. So in the future, this is how we're going to show polar. Okay? So this is called a polar covalent. And what we'll do in the future, we're going to go ahead and show it like this. You guys don't have to show it in your notes. But we're going to show P, and we're going to show a line for a bond. And we're going to have it bonded to S, so that line's kind of like they're hooked together. And we're going to show a little dash, meaning they're hooked together. And then what we're going to do, we're going to find the one with the higher electronegativity, which is sulfur. And then what we're going to do is draw the arrow toward the one with the higher electronegativity. And then what that does is it says it's polar. And if you notice on the tail, it looks like a plus sign. And on the arrow, that would be the opposite of the plus, which would be negative. Okay? And then that tells you that this is polar because one side slightly positive, one side slightly negative. Okay. We also will see these kind of drawn to where we'll put circles around the positive side, we'll put a circle around the negative side. And this side is positive, that side is negative. Okay, but we'll get into the symbolism of polar later on, but just to let you know, polar bonding is important in a lot of other characteristics. Okay, when we talk about molecules that want to tend to come together. Okay, how about N and Cl? Bubba, did you get an answer for N and Cl? I like both. 0.12 nonpolar. Well, that means that when that bond forms, there's not much difference in electronegativity, and it's equal charge on both sides. You know, it's just basically neutral on both sides because there's not an unequal share, not enough to create a polar bond. So nonpolar covalent. Good. Okay. Alexis, what'd you get for I and P? 0.47 polar. Still probably not very polar, but it's in that category where it's kind of like having a weak magnet. So if something's a weak magnet, the opposite sides are not much difference in polarity. That's what always happened to me when I had physical science and was doing some things with physical science and magnets. They'd always lose their polarity. And then I go to use them, and they weren't very good. It was just like, really? And then I bought a magnetizer where you can put the south side in there and magnetize it and reuse those metals like iron that are magnetic. You could reuse them, but it's like having a weak magnet. Okay, not very potent. Right? Barium and oxygen. Scott, did you get that one? What'd you get? What's that? Ionic? What was the difference? What is it?
2.5.
That's highly ionic. That is something that would definitely have, if you look at characters, you know, being ionic, that is going to have all those characteristics. Okay? Okay, so now you can do that. If you had a quiz like on Thursday or Friday, and I had you say, all right, I've got a list of so many elements, the combinations, tell me if they're ionic or polar covalent or non-polar covalent. You could do that. Okay? You should be able to do that if you remember those numbers. And even if you don't remember the numbers, at least you could figure ionic and covalent based upon the 50% line. Okay? All right. So, what we're going to do now is have you guys write down some terms. So in this definition we have a molecule. So what's a molecule? It's a neutral group of atoms. Do you guys know what atoms, what area of the periodic table these atoms are located? Where are these atoms located that make up covalent bonding? What's that? Well, noble gases won't bond. Well, because you know, we'll talk about why noble gases won't bond, but noble gases would not be included in these molecules because they don't tend to form bonds. Okay? So look back at covalent bonding. What type of elements or atoms came together in your definition we did yesterday? Nonmetals and nonmetals. So these are strictly just nonmetals put together. How big a choice do we have? We don't have very many nonmetals. Carbon's 1, nitrogen 2, oxygen, fluorine, phosphorus, sulfur, chlorine, selenium, maybe, bromine, iodine. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We only have 10 elements that are included out of the 90 that would be molecules. Okay? 90-something% of all chemical formulas are molecular, made out of just those 10 elements. Okay? So 90-something% of everything is molecular. Not near as much ionic. Ionic is a lot less. We look at our body, what's in our body, 90-something% is molecules. And we're made of these. So it's kind of important to know a little bit about molecules. Medicine that we take, antibiotics, steroids. Now the steroids are good, right, because they help the body heal faster, okay, get over sicknesses better. 90-something% of, probably almost 100% of all medicine is molecular, okay? If you're going to be a pharmacist, that's what you're going to study, organic chemistry. It's a killer in college. It weeds a lot of people out of taking chemistry later on in life. They say, I don't think I'm going to be a chemistry major anymore. This organic, way too tough. I'm not going to do it. Okay? And it weeds a lot of people out. Okay? They decide, I really don't want to work that hard. I don't get it. I'm not going to be a chemist. I'm going to go and do something else. Okay? But it's pretty much molecular. That's all you're studying. Okay? Chemical formula. This is just for everything. Everything ionic or molecular, this definition goes with. It tells you if I have sodium chloride, it's NaCl. That's a chemical formula. It tells you the subscript or tells you the symbols, and if you had subscripts, let's see, I'm trying to think like something that's ionic would be baking soda. Baking soda is NaHCO3. That's ionic. It's got a metal and some nonmetals hooked together. Okay? It's baking soda. Sodium chloride. Okay? Limestone. CaCO3. That's limestone.
What is the 3 again?
The 3 tells you how many you have of that element it's directly behind. So we have 3 oxygens, 1 carbon, 1 hydrogen, 1 sodium. Here we have 1 calcium, 1 carbon, 3 oxygens. So whatever the subscript is, tell you how many of that atom you have. It's just written lowercase. But we also have molecular, which is H2O, which is CO2, which is glucose, C6H12O6. So those are all nonmetals hooked together. Okay? They're all nonmetals hooked together. So that would be considered a molecular formula. Okay? Those are molecular formulas. So I have models up here. This is water. It's H2O. Okay? This is ammonia, NH3. Okay? CO2. Okay? This would be CO2 that we would have. You guys get to play around with these. This is CO2 has a double bond when we look at CO2. So carbon oxides, 1 carbon, 2 oxygens, 2 nonmetals hooked together. We look at the difference in electronegativities. We're going to find out that it's going to be covalently bonded together. Okay? So CO2 would be this example. You guys probably get to do this around Thursday or Friday at CO2. Okay? And so those are just molecular formulas. So I'm really just going to talk about all molecular formulas today. Okay? So you got 4 definitions. You know which ones are ionic, which ones are polar covalent, which ones are non-polar covalent. You know all of that. What I'd like you to do, get a book, and you have it in front of you, because you'll do definitions. Turn to page 183, if you would. 183. Okay, I'm going to show you a hard way to show bonding. Don't write this down. Okay? Don't write this down because you're not going to use it. If I wanted to show this bonding, this ammonia, NH3, this is how I would show it. Showing the orbitals and where we're having sharing taking place. So nitrogen. Nitrogen is going to be 1s2, 2s2, 2p3. We're not concerned about this S2 because it's an inner shell, only worried about the outer shell. So there is nitrogen. Here's hydrogen, 1s1. Okay? So I want to bond these two together. All right? So where can hydrogen go? Where can that electron go? What's that? In the P. So we're going to go ahead and put it in the P. That's the arrow should be going up. Okay? Does nitrogen have an octet of electrons? Because to show bonding, everything has to have a full outer shell. Now, hydrogen won't have an octet because it only requires 2 electrons to have a full shell. Because it's that first shell only has 2. So now it has 6. How else are you going to Can we bring another hydrogen in here? We can. Okay? So we can bring a second hydrogen in there and show bonding. Does nitrogen have 8? Does it have 8 electrons in its outer shell? 1, 2, 3, 4, 5, 6, 7. So we bring another hydrogen in. So it can have 8. Does it have full outer shell now? Does all the hydrogen have a full outer shell? Okay. This is what we call sharing of one pair of electrons. And now nitrogen's outer shell is 2s2, 2p6, and it's said to be stable. All of these are 1s2s now, because they're sharing in this location in those 3 spots. So here is ammonia, right here. See it? It's ammonia. Okay, 3 hydrogens bonded off and then 1 nitrogen. Okay, now that's not an easy way to show that. There's a much easier way to show that, and I'm going to show it to you tomorrow. But that's sharing. They're sharing the same orbital. And when they're sharing, that's called a single bond. So this is a single bond. And we can show single bonds with just wooden dowels on these models. This is the double bond. So we would show sharing of 2 pairs of electrons between 2 atoms, and I'm not going to show you that today because you're not going to have to draw these that would be that way. Okay? So the last thing I'm going to go through with you is this called this dot notation, because the dot notation is going to be easier than drawing all those arrows and doing electron configuration. So turn to page 184. So let's say we take that same nitrogen, all right, and we want to show an easier way to show where those arrows are at. So I'm going to draw the symbol nitrogen, okay? What I'm going to do is, we know that, now you won't have to do this, but I'm going to go ahead and draw it out again. We have the 1s2, the 2s2, and the 2p3. And we want to just show the outer shell electrons. So we just want to show these outer shell electrons because those are the ones involved in bonding. We don't want to do anything intershell because they're never involved in bonding. And we want to show those 5 electrons around nitrogen. How do we show it? Well, we would show it the same way as we do orbital notation, but we do it with dots. Okay? So here's the orbital notation for nitrogen. So what we're going to do is, if we have 2 or more electrons that are in the outer shell, we'll pair those first 2 up. Everybody knows why we pair them up, right? What does this pair symbolize? Which of these orbitals does that pair symbolize? The S2. So anything 2 or more, we know it has an S2. Okay? Then these 3 here, we're going to go ahead and fill in at the corners, or each 90 degrees we'll look at filling in an electron. So this is the electron dot notation for this orbital notation. Any questions with that? So this will be easier to write than the 2s2, 2p3. Okay? So what I want you to do is practice, and I want you to see if you can come up with the correct dot notation based upon the electron configuration. Now, you guys have electron configurations written out for you for all those elements, right? You have the shorthand or the noble gas. So I'm going to give you a list of 5, and I want you to draw the dot notation around them. I want you to see if you come up with the correct one based upon
So wait,
the idea.
why is there 2 dots at the top?
That symbolizes the S2.
What about the 1s2?
That's the inner shell, and they're not involved in bonding. We don't We don't look at anything inner shell. So when you guys look at your configurations, they won't have any inner shell ones that they would have. If they do, they're Ds. And Ds are all inner shell. Never going to be outer shell. Okay? Alright, so these are the ones I want you to do. I want you to do chlorine. I want you to do carbon, phosphorus, selenium, and argon for tomorrow. Now, they do have some reading. So if you don't understand electron dot notation, they tell you there the valence electrons, which are the outer shell electrons, how many you have, and what it should look like. Now, if you notice, they're doing it different than I am. They're just showing dots separately. I don't want you to do that. I want you to show it based upon how they fill the subshells. Okay? So if it's 2 or more, you're going to pair them up. If there's 2 or more, you got to pair up at least one of them. Okay?